program on invariants for resonantly interacting waves.
Thank you very much, Keith.
Sergey.
Okay, so thank you as well for organizing such a great program from which I learned quite a bit and realized that I have a lot more to learn. So, yeah, and of course it's a great honor to give a closing lecture. Actually, yeah, looks okay. Anyway, so at first I was very interested in the program, but of course I knew that I did nothing on topological aspects of fluid dynamics or any other science, and so I decided just to listen. But then finally, I thought, well, that work that I'm doing actually has some topology in it too, some geometry, and so you might find, or not, some links to the current program. So, anyways, that's work with my PhD student Katie Harper and Miguel Bustamante, who's a lecturer at UCD. So. Basically, let me skip a table of contents. What I'm going to be talking about is a system of waves, weakly nonlinear waves. Essentially, well, of course, the first example that comes in mind, water waves, right? But I guess in this particular talk, I will be concerned with three-wave systems. So if I consider water waves, they experience four-wave mixing. Okay. Although if I consider waves that are caused by surface tension, they will be three-wave mixing. But my major example will be Rossby waves, planetary waves that are in, say, Earth atmosphere of the scale of 1,000 meters long. Kilometers, sorry. Of course, thank you. So the ansatz I will consider is in which I ignore all the losses and forcings of waves. So it will be a Hamiltonian system. Okay, and in Fourier space, I can write equation for wave amplitudes, which will be generally complex functions, right? Which takes a Hamiltonian form like that. So basically, I take a functional derivative of the Hamiltonian representing wave energy, and Hamiltonian consists of parts, starting with quadratic part, which corresponds to for linear dynamics. So which means if I take derivative of that, I will have linear term which describes oscillation of amplitude A with frequency omega, which will be a function of k. So it's a dispersive waves which, frequency depends on wave number k, and plus I write it in the terms of expansion and wave amplitude. I have terms that are responsible for nonlinear interaction of waves. And so in my talk today, I will be concerned with systems weakly nonlinear so that I can truncate my system at this cubic Hamiltonian corresponding to quadratic nonlinearity in equations for evolution of waves. Right, okay, so here, the shorthand notation, delta stands for delta function of k's. So also what I'm going to do, I'm going to consider periodic box for simplicity, right? So d-dimensional system, d being 1, 2, or 3. And in periodic box, of course, Fourier space is discrete. So I'll have a d-dimensional lattice, uniform lattice of wave numbers, okay, and therefore the the Fourier so the nonlinear terms or you know, terms in Hamiltonian will be sums. So if it was a continuous Fourier space, if it was infinite box, that would be integrals.
What do you mean, sigma 1, 2, 3? Is that cyclic, 3 terms in which
That,
you
just definition.
permutation or something?
No. This is just definition, delta function of k. So basically, it's a Kronecker symbol. So because I consider sum, it is just discrete delta function. So
that's your phase matching condition, effectively, right?
no, this is just a Fourier space. I mean, you take any PDE, nonlinear PDE of quadratic nonlinearity, Fourier transform it, and you will have this delta function always, right? It's convolution term that always contains matching of wave
So
numbers.
it's a sum over all triads of that resonant triads.
Yes,
But
but they are resonant only in wave number right
Yeah.
now,
Yeah.
right? So in wave number. So there is nothing here about waves. Take Navier-Stokes, take any other nonlinear equation, you will have this in Fourier space, this delta function, right?
Absolutely, but I mean, one example of this is when you do, for example, frequency conversion in optics, and then you have plane waves. So those k's are your plane wave k's, and then this is effectively a constructive interference condition between the 3 wave vectors.
Yes, you know, for waves, of course, so we will see a little bit later. This also resonance in omegas that you have to, you know.
Yes, you also have to worry about those. But typically, for any finite size system, those deltas become spread out. They're no longer a delta function.
No. This don't spread out. These are just, you know, this is just exact. I mean, take your PDE in periodic box, Fourier transform it, and you exactly have that. This is just, you know, property of Fourier transform. Percival theorem.
This is simply that you chose to expand Hamiltonian in such way. But
No.
Spread.
This is has nothing to. Okay, so basically, all right. Well, if you wrote what equation corresponds to this Hamiltonian, that would be quadratic sum over 1 and 2. So and 3 would be external variable k, and so that would be just quadratic nonlinearity, right? So if I kept going, so the deltas will be also there, but they will be involved in 4 wave vectors. If you Fourier transform quadratic nonlinearity, you have 3 wave vectors matching condition. If it is cubic, of course, it's 4 and so on, right? So this, yes, so I truncated at the quadratic, and so it's like that. But but let's postulate the system as such that has quadratic nonlinearity. Well, Navier-Stokes has quadratic nonlinearity, right? So let's at the moment, let's think of it almost like Navier-Stokes.
I was just worried about the notation. I mean, normally if I have a sigma, I think of it over things like I, J, and K, with I, J, and K running from. And this notation is
yes. So perhaps I would another way to write it here, get rid of that and say K1 plus K1 plus K2 equal to K3.
Yes.
That's the same. So, yeah, of course. Yeah. And so again, shortcut notation here, interaction coefficient, which is a function of 3 wave vectors. Again, as you know, in Navier-Stokes it would have a specific form, but for wave systems of various kinds, they will have their own form. So the different systems here are characterized by different forms of frequency dependence on k, dispersion relation, and different types of nonlinear interaction coming through the interaction coefficient. So now, if I consider, well, basically, as I told you, for very weakly nonlinear waves, I can ignore nonlinearity, and it would be just a wave amplitude oscillating with frequency omega. And prefactor of this wave would never change in amplitude, right? So then, if I consider next order, weakly nonlinear system, I introduce so-called interaction representation variable so that I separate slow time dependence and fast time dependence. Fast corresponds to linear oscillations, and slow due to nonlinear interaction, right? And if I substitute that to my Hamiltonian equation in terms of new variable, then I get rid of the linear term. But I will gain in my nonlinear term, I will get oscillating factors, right? That should be familiar to you. It's a standard kind of Schrödinger versus Heisenberg representation, right? So if you are in Heisenberg representation, you know your matrix coefficients will start depending explicitly on time, right? So now, but you see, this has fast oscillations here, and essentially, if the nonlinearity is so small and these oscillations are so fast, then the mean effect will average out to 0 for all these modes which are not in exact resonance in omega. So unless this factor over here exactly goes to 0, so that we don't have oscillation, right? We have cumulative action, cumulative effect, right? Then the rest we can ignore. Okay. So here's actually this. There is a specific condition on how when we can do that. Depends what area of science you're coming from. You maybe understand it from dynamical systems point of view. This is just when we have phase space and we have, imagine your linear system, it's an integrable system, right? Obviously, I mean your phases are just rotating with frequency omega, and amplitudes are not changing. Angle phase variables, right? So you have in this multidimensional space corresponding to wave amplitudes, we have invariant Tori that you know it's just full of it, full multidimensional space, right? So then, when you have resonances, this at the resonant surfaces, you start messing this irregular periodic motion. You start messing them up, right? So essentially,
can you assume the not exact but small deviation comparable with nonlinearity?
Okay, so that's precisely what I'm trying to say right now. So basically, applicability of ignoring these fast oscillations is that the spreading of the resonance due to nonlinearity. So this thickness of the stochastic island around, or stochastic sort of separatrix in between of regulatory stochastic area, right? So the broadening of the resonance has to be smaller than the distance between the adjacent modes on our periodic grid, right? So remember, we are on periodic lattice in Fourier space, right? We have discrete modes, right? But if say the broadening of the resonance is smaller than space in between the modes, then we can leave only the exact resonances, right? And ignore that there can be quasi-resonant interaction due to the nonlinear broadening. But if the broadening is approaching the space in between the modes, this means the quasi-resonances will be as important, yes. Yeah. And then we come to another description. We come to so-called wave turbulence, where we can write kinetic equation. So this is not wave turbulence. in a classical understanding of that. So wave turbulence is an infinite box limit where the spacing between the adjacent K modes is small, so that even small resonant broadening, nonlinear broadening, is still a lot bigger than distance between the adjacent Fourier modes. And this is the opposite limit, right? This is the limit where nonlinearity is so small that it can really ignore quasi-resonances, only exact ones. Okay.
But so is there some dimensionless? I mean, what number should I think of as telling me when I'm okay? Because
yeah, so there will be a number which is basically associated with the amplitude of the waves, right? So when amplitude is getting bigger, the broadening is getting bigger, right? I have to, you see, so the...
can you think of it sort of perturbatively as 1 over delta t gives you the width of the coupling between different energies?
1 over delta t, which is delta t?
If you start time at some point and then you call time delta t.
Mm-hmm.
So 1 over time gives you the extent to which different frequencies mix. But then there's a second time scale, which is the rate of energy transfer between frequencies. And I guess when one is much faster than the other, that sets your different regime, or is that a bad way to think?
Okay, well, that 1 over time sounds a bit, kind of, that I don't know what physics to attribute to it. So think of this, okay. You have wave packets in a finite box, right? So these wave packets propagate coherently only until nonlinearity will mess the phases up, right? So basically, you can think of wave packets as particles, right, whose mean free path is set by nonlinearity, right? If this mean free path is less than the box size, right, you can ignore all effects that are because of the finite box. You can ignore the boundary conditions. This box will be opaque medium will be opaque with respect to such particles, right? Then you will be in the wave turbulence situation. Then you will actually, your resonant broadening will be bigger than the adjacent distance between the modes. It's just reformulating what I just said in Fourier space, reformulation to the physical space. So if, on the other hand, wave packet, its nonlinear interaction is so small that it can bounce many times between the sides, boundaries of the box, then it forms a standing wave, right? And so it remembers very clearly about its discrete nature, of eigenstates. So then we are in this regime. So it's basically like, shall we say, like set of standing waves, except here we have periodic boundary conditions. We don't have standing waves. It would be if it would have reflective boundary conditions. But okay. Anyway, so now, so let me just postulate then that I can ignore all the oscillating terms and leave only terms that are in exact resonance and frequency, right? So thus we have two resonances satisfied simultaneously. Wave numbers that we discussed, just nothing special, that's just property of Fourier transform. And the frequencies that are simultaneously resonant. And we come to this equation in which I, of course, forgot to write one other delta. No, here it is. So two delta functions. Now, this is wave numbers, this is frequencies, right? So, but one thing we can observe straight away here, it's no longer a weakly nonlinear system. It's a strongly nonlinear system because the linear term is gone completely. And we forgot completely about the will wake up. Maybe I should spend less time on one slide. Okay. Hmm? Yeah. Okay. So, we actually, apart from this selection, you see this delta function select out of the entire sum which modes will interact, right? Apart from this selection, there is no other role played by frequency anymore. So if for some reason different types of waves with different frequencies select similar subsets of interaction waves, they will have exactly the same properties. So what are these subsets of waves? It turns out that if I select a mode K here, right, and see with which waves out of this sum does it interact, it turns out that in many systems, including Rossby waves, that these sets are finite. It could be starting with single triad. It could be such that I choose K, and there's only one set, K1 and K2, that's in resonance with this K, and no others, right? Or it could be that two triads are connected. I choose K, and it's connected to K1 and K2, but in turn, some of this K1 or K2 connected to something else. But then they may be disconnected from everything else. So it could be two triads connected together. It's like two triangles connected together. It's like a butterfly, right? Or it could be bigger clusters of waves. So
those are the properties of V you are talking about?
And that's
couples the modes.
V couples the modes, yes. Of course, for these modes, we assume that V should be non-zero, finite, yeah. And so you see, so this means that for such systems, the interaction, the evolution of the sets of modes splits into independent evolution within clusters of various sizes, starting from individual triad to butterfly to larger triads. And clusters don't exchange energy between themselves, don't interact. So, okay, so here's a schematic representation of a butterfly. So basically, if I okay, so it's one triad A, another triad B, and that's its amplitudes. And in this particular case, it's connected via one amplitude, which 3A and 3B, it's the same wave number. It's the same wave mode. Okay, so basically, the way I denote it here is the wave which is here, 3, will be at the vertex, and the K1 and K2 will be at where the arrows point, right? So it's basically, it's like K3 is decaying into K1 and K2, right? So you see, they are within the triad, they are not equivalent one to another. So one comes with plus sign, two others come with minus signs, right? So one is decaying into two other. And so this is kind of notation. Now, for Rossby wave system, that's the cluster, so in the very first slide, so basically there's a lot of individual. So this is a Rossby wave system, and let me see actually. Yeah, so this is just illustration for now. I'll come back to this system. So it's just to illustrate the clusters can actually connect to much greater sets. And so we have an interesting system for large clusters where the number of degrees of freedom is large but finite. We kind of have a mesoscopic, if you wish, system when you expect a complicated, chaotic, turbulent behavior, right? but so it's large. Number of Fourier modes is large, but it's still not a continuous system. It's still a system with a structure in Fourier space. Not all modes on the Fourier lattice are equivalent. Those are in resonance selected in these clusters.
Existing cluster depend on dispersion relation.
Yes.
So
Yeah,
you must
can you
give the
remind us?
dispersion.
Exactly. That's
relation.
yes. Okay. So let me see if I have it here. I sure have it here. Okay. Maybe not. Okay. So yes, I'll give it to you right now. So basically, for Rossby waves, the dispersion relation is kx divided by 1 plus k squared. So it's x squared plus ky squared. So x is a wave number along east-west direction, and y is south-north direction. And so, I consider two different limiting cases where, well, okay, so this is in dimensionless form. Okay, one is actually its dimensionless representation of a Rossby deformation radius. So if I consider k rho much greater than 1, so I arrive at dispersion relation like this. Or and that's very commonly considered in atmospheric sciences. This kind of Rossby waves, you can think of it's Rossby waves with a rigid lead. Okay, so if there is no if a lead is rigid, then this one disappears. And in the large scale limit, when k rho is much less than 1, so correspondingly we do Taylor expansion here, right? And so we have omega equal to kx, and then I Taylor expand, it will be 1 minus k squared. But you see, from the point of view of resonant conditions, can you see here? No. No. Okay, so from point of view of resonance conditions, this term I can throw out because it's already taken care of by resonance in k. And I can just simply leave omega equal to minus kx k squared. And so this is for this dispersion relation for large-scale Rossby waves that I have that. So it's waves that are longer than Rossby deformation radius, which is about 100 kilometers. Okay, so let's say 1,000.
It's amazing that such a simple dispersion relation can give such a complicated picture.
Yes, in fact, I mean it has very deep mathematics in it, in terms of elliptic curves that Miguel is right now exploring. So, but for me, I just experimentally choose a set of, let's say, 100 by 100 wave numbers, and I experimentally, well, with numerics, just find those modes that are exact resonance and look at these clusters, right? So, okay, well, let's come to consider dynamics of clusters, starting with the most elementary one, which is just one isolated triad, which is it's a well-known nonlinear system. It's a well-known integrable system, okay, and it's integrable because it has three integrals of motion, right? It has, well, Hamiltonian, obviously, but two Manley row invariants. So Manley row, they were electrical engineers, and so they discovered the invariants in electric circuits, including the valves, And so, and a lot of the theory of oscillations came from that particular, sort of well, systems in mind, But so yes, so three modes coupled and Manley row invariants. Basically, you can think, that the number of quanta, the number of waves that are lost by at wave number 3. Okay, if one is lost here, then one will come here and one will come here. So the sum of B1 and B3 would be constant, and sum of B2 and B3 will be constant, right? So easily checkable by just simply multiplying that by complex conjugate of B1 and adding to complex conjugate, and so creating combination of these integrals, so it will all cancel out. So the second simplest cluster is a butterfly. And okay, so we have 5 equations for that, because there are 5 nodes, right? Well, 3 at each triad, but 1 is common node. And here we have 2 Manley row invariants as before, but we also have additional one that contains 3 amplitudes, right? Okay, so yeah, so sorry, I forgot to say here. So integrability comes from the fact that 3 invariants, and we have 3 complex amplitudes. So the entire phase space is 6-dimensional. So in Hamiltonian, and these invariants are independent in involution, and so this is a classical example of integrable case. Whereas in this case, we have 3 invariants plus energy, so 4 invariants. But the system has 5 complex variables, right? So we would need one more to integrate, and we don't have it. And so it's non-integrable. And if you put it on a computer, you see some chaotic behavior. You can, of course, choose some subsets of motions that will exhibit some interesting periodic behavior. But generally, it is chaotic.
General question. So when you claim something's non-integrable, that's basically a non-existence result.
All right, yeah. Okay, sorry. Maybe exactly. So it's I should not say that. Maybe it is integrable, but
Data suggests otherwise.
Yes, right.
Are those integral connected to some symmetry of the system that you can specify, or?
Yes, I'm coming to that. That's the subject of my talk. Yes. Okay, so basically, now just let me introduce one very simple auxiliary object, just to write things in a more concise way, so-called cluster matrix. Basically, cluster matrix, if I have a cluster which consists of m triads with a totally of n modes, right? M triads and n modes. So I construct a matrix n by m in such a way that each row corresponds to a triad. Okay, each column corresponds to a node, and then each node for each triad it consists of mostly zeros, apart from 3 entries corresponding to modes that are in resonance, right? So for those, I put -1 if it is at the vertex, and 1 if it is at the end. So if I have modes like that, right? So say this is K3, this is K2, this is K1, K3 equal to K1 plus K2. So here I will put -1 at the entry in my matrix. Here put 1, and here put 1. And the rest are 0. Okay? And so, and then in this case, my resonant conditions, I can rewrite using this matrix just like this. Right? Just as a as a set of linear equations like that. Indeed, so if I write this out, so for each m, m representing a row, representing triad, I will have condition on k so that only 3 elements in the row, not 0. And so I'll have it like that. But out of these 3 elements, one is -1 and the other one 2. And so I recover my resonant condition. And same for omega. Exactly.
In different matrices, no?
Different matrices for different clusters. So
For K and omega.
no, it's the same.
It's the same.
Because it's the same resonant condition. For same modes should be in resonance, right? So, and now this is a very simple theorem relating, how these invariants come about. Okay. So basically, let's consider, well, we have a discrete set of wave numbers, right? Let's number them by n. Let's suppose we have a function phi of these wave numbers, right? So let this be a real function of wave numbers of modes of the cluster, right? And let it satisfy the resonant condition. Same resonant condition as wave numbers and frequencies for each triad in the cluster, right? So essentially, what I'm saying, if we have a resonant triad, i.e., wave numbers and frequencies satisfy a resonant condition, the same resonant condition should be satisfied by this new function that I introduced. Then in this case, the quantity defined like this will be invariant, quadratic invariant. Will be exact quadratic invariant for this system. So, and phi will be density of this invariant. Obviously, from this point of view, I can choose phi to be a wave number, and that will be invariant, right? Because wave number is a satisfied resonant condition. And that we can interpret as momentum of the wave system. Okay, it will have the number of components, it will be vector invariant, number of components corresponding to dimensionality of the space. Or I can choose omega, and that I can interpret as energy conservation. So the proof is very short. So essentially, to prove, I just differentiate the quantity that I wrote and substitute b from the equation. Okay, and if I substitute b from the equation, substitute b dot from the equation, and so and then I change variables, change indices within, play with indices within the sum. So I can see that I can now factor out a combination of phi's like this in a bracket. And I see then, and that proves the theorem. So if for every triad in this sum, this bracket is 0, then I dot is 0. So want to emphasize here that it actually, the fact that the system is Hamiltonian is important here. Because when I change indices, it's important that, particular form of the nonlinearity that is in Hamiltonian systems, it has certain restrictions, symmetries. Okay, but now you see that because of because in our theorem we have this condition, resonance condition, then basically we need to solve this equation to find all phi's that satisfy this property. And this is nothing but finding a null space of matrix A. right? So this matrix A that we introduced, if we find its null space, we find all the quadratic invariants. Okay. So we can, yeah. So let's just also for notation introduce. So if I find null space, and that will be each of the vectors of which will be given the set of phi's, right? So given one invariant. Okay, and then I can put these vectors side by side and create what I call null space matrix. It's just convenient representation of all the invariants if I show the matrix, and all the columns of which will represent invariants, independent invariants. Obviously, because they are independent invariants, any linear combination will be also an invariant.
So your space of quadratic invariants are linear space.
Yeah.
And what about its dimension?
Okay, coming to that. Yes. So actually, right here. So basically, the dimension, right? So the number of independent invariants, right? Well, you could generally, kind of most typical case would be n minus m, right? So it's a rectangular matrix, right? So n is a number of modes, and m is a number of triads. M is typically significantly less than n, right? Number of triads less than modes. Well, originally each triad had 3 nodes, right? So, and so you would think n minus m is a typical case. And a lot of times this is actually the case. But sometimes, and I will show you it a little bit later, that we can have we can have less independent rows, m star, and so we can have more invariants than just difference between its dimensions, n minus m. But still, think of it, n minus m, if this cluster, like this frog, is big, n minus m is a big number, so it's a lot of quadratic invariants for a large cluster.
But not enough to make it integrable. Huh?
No, unfortunately, yes. Or maybe fortunately, so it's more interesting. So, yes, okay, so there's some properties. So this is what I just discussed. Another one, that in order for clusters to be connected, right? So, so there's obvious restriction that 2m plus n should be greater or equal than n. So this is kind of limiting case when you have a chain of triads connected like that. So if I try to squeeze in just one, okay, so if yes, so if I try to squeeze one more node, I would not be able to do that without taking it into 2 independent parts, this cluster. So this is a simple rule. So another one, also simple, that because each row of A consists of 3 entries, 1, 1, minus 1, and the rest are 0, from combinatorics, the number of possibilities for such rows is less or equal than this value. But this is a great overestimation. Usually, the resonant condition sets it at much smaller number. Now, okay, so basically, let's introduce dimension of a cluster, right? So basically, we have dimension of embedding space, d small, but dimension of a cluster is the dimension of a polyhedron formed by the cluster, right? For example, individual triad would have dimension 2 even if it is embedded in three-dimensional space, right? Because it's three nodes always in a plane, right? Okay, so then the total number of invariants. So there is another condition that the total number of invariants has to be greater or equal than this dimension D, dimension of the cluster. Why is that? Because we have, by construction, K's given invariants. This is momentum that I mentioned, right? And K has components. And the number of independent wave numbers is a dimension of the cluster, D, right? Okay, so you see, each component of wave vector satisfies a resonant condition, right? So generally speaking, there will be, say, in D-dimensional space, D resonant conditions like that, independent, right? But because cluster can be actually two-dimensional in three-dimensional space, right? So the number of independent resonant conditions on K will be less, will be actually D capital rather than D small. So from the condition that we must at least have those invariants, the momenta, there is a restriction that this is bound for the number of invariants. For example, okay, so for an isolated triad, so the number of invariants is 2, as we mentioned. It's a Manley row invariance, right? It's consistent with, so it actually is consistent with this resonant condition because simply D capital is equal to 2. So it's the isolated triad is either on the plane or it can even be a collinear triad. It could be on the line. So, okay, so let me just keep that, maybe it's not. So there are some exclusion principles for matrix A, right? So that not all the combinations, not all possibilities of a construction of the set are possible. For example, it's not possible to have same non-zero entries at the same columns. For example, it's not possible to have 1 minus 1, 1 minus 1, because this would mean that the third wave number would be exactly the same entry 2, and that would simply be the same triad. Okay, and or this is also impossible, 2 entries like that, for the same reason. But also, if the original variable in physical space is real, so this would also be impossible, because we associate for real variables k and minus k are not different things. We have a condition that if original variable in physical space is real, so then k star is equal to a minus k. So k minus k is not a different wave number, and so for the same reason, this combination would also mean it's just exactly the same triad. So okay, so now let me give you an example. So here's Rossby waves, and this is a Charny-Hasegawa-Mima equation, also known as a quasi-geostrophic model, also known as beta-plane approximation, beta-plane model. So that's the dispersion relation that I wrote. Okay, that's nonlinearity given by Jacobian, like quadratic nonlinearity like that. So in the two limits that I wrote here, small scale and large scale, okay, well, so if I consider small scale limit, and simply just take it. So the in the limit, my dispersion relation becomes like that. And so if I just simply take k running from minus 100 to 100, and notice here I run it only from 1 to 100 because for this reason the original variable for Rossby waves is real in physical space. So I only need half of Fourier space in order to describe the whole system, right? So I choose half of Fourier space being positive kx greater than 0. And also I exclude kx equal than 0 because they are not waves. They have 0 frequencies here, if kx equal to 0, right? So that's for this reason I choose only, only positive kx is here, and whereas ky goes from minus 100 to 100. And so in just by checking, I see which I construct my clusters. And what I see this. I have a lot of triads. Okay, I have 34 clusters, out of which 24 are isolated triads. Okay, so only one is shown here. Okay, 4 butterflies. So out of them, 2 shown here, and 2 others are obtained by symmetry ky to minus ky, because everything is symmetric in this system with respect to change ky to minus ky. Okay, and also 2 triple chains, 3 triad clusters, 2 7 triad clusters, this one and also mirror symmetric, and 1 13 cluster. So you see, most of them are individual triads. They just don't interact. They are integrable systems. So if energy happened to be only in those modes, that would go nowhere, and it would just regularly oscillate in them. Whereas out of bigger ones, only actually small number of bigger ones are present. But how they behave, that's interesting, right? So whereas if I consider now the large-scale limit, okay, so this dispersion relation, I see that they're connected in much easier way. So they connect much better. So there's only 2 isolated triads, turns out. Okay, and this 1 10 triad cluster. And the rest of them are connected in 104 triad cluster. And here you notice I choose k much less. Okay, so even for this smaller range of k's, they're very well connected. Now, these are the large-scale Rossby waves. This means larger than deformation radius, larger than 100 kilometers, but obviously less than the radius of Earth, right? So let's say we're talking about scales of 1,000 kilometers, right? And obviously, because it's not too far away from radius of Earth, discreteness is important. Of course, on the sphere, resonant conditions and everything becomes different. But if we, if we simply think, that our beta plane is the simplest model for a sphere.
So is that range of k's that you've chosen realistic for the Earth?
Yeah.
Looks about right.
Yes.
Yeah.
Yeah. Because you think, between 100 kilometers and several thousands. Right?
Yeah.
So, and for 10 triad cluster over here, right? Just this is a simple exercise on MATLAB that give us, okay, first of all, we create our matrix like that. You see all the entries 1, 1, minus 1 in each row, like that. And it gives us null space. I mean, it has no problem to do that very quickly. What we notice here, so is there any structure within this, each column represents invariant. You see, for example, the first column, it has only 2 non-zero entries, and the rest are 0. This is precisely like a Manley row invariant for individual triad, right? And we have another one like that here, with only 2 non-zero, and another one here, and another one here. So you can basically, this means that this invariants, they correspond to within the cluster. They correspond only to individual triads, so they are not affected by the dynamics of the rest of the triads, but they are very local, right? So we are trying to identify now, which conserved quantities, where do they live on that big cluster? And it turns out that these particular invariants live on those triads that have 2 loose ends. Like this one has 2 loose ends, not connected to anything. Second, third, fourth, fifth, sixth. So there will be 6 invariants of this kind. So whereas you see other invariants have a more complicated structure, right? Have more. So basically, I don't know. I mean, probably I should not go that much further. So maybe 5 minutes more or something?
Yeah.
Okay. Basically, what I just said about that invariance can be attributed to particular structure of the cluster, such as like having 2 loose ends, right? You can go deeper on that. You can have identify invariance a little bit more complicated with a little bit more complicated structures. For example, as with structures containing 2 triads connected in a particular way. So 2 triads connected with 2 modes and not which are not connected to anything else within the cluster, for example, right? And so essentially, this gives us an algorithm how to reduce properties of a large cluster in terms of properties of a smaller cluster. Okay, well, I'll just show a simple thing. Okay, so imagine we have in our cluster a node which is belongs to only one triad and not connected to anything else. Let's renumber this node to put it at position 1. It will be number 1, and let's this triad to be triad number 1. So it's not connected to any other node. This means it will be just like that. And we see that because of that, this row is completely linearly independent of all the others, right? So then I can, what I can do, I can consider a smaller cluster. You take this triad out, which has 1 loose end. Take it out, and I'll have a smaller cluster, smaller by 1 triad, right? Which I call its matrix I call A prime. So and for this, so like this, and let's denote the positions of the other nodes in the triad N and M in the triad that I just eliminated, right? So this is the original problem of finding the null space, matrix A. Okay, A prime. But then if I find null space for matrix A prime, for smaller matrix, then I can find the solution of the original bigger problem simply like this, because the first row will give us condition like this, resonant condition for the first triad. And so if I found these entries for the smaller matrix, so then the other one, the first node that I eliminated, I simply put that. You know. And these are the entries somewhere inside here that I found. So, but what's important that the number of invariants of the new matrix A prime is exactly the same as the number of invariants for the original one, because I took away one row, one column, and that I took away one linearly independent row, right? So I did not change rank of my matrix, cluster matrix. So okay, I can keep doing that, right? I can a lot of a cluster may have a lot of loose-ended triads. I take them all one by one. By taking them all out, I may have new ones, you know, that free become with loose ends. So I take them apart like that. But then I may come to a situation when all of the nodes are connected to somebody else, and then I remove not just one triad, but I remove pairs of triads. I remove blocks. So here's illustration, such that the two nodes are connected within the triad, but not to something else. This means that if I call these triads number 1 and number 2, I have, well, in the top left corner, I remove blocks 2 by 2 like that, or maybe with possible permutation of -1 over here. And if it's easy to see that these blocks also represent linear independent. So by removing those, if everything else below is 0, okay, so removing 2 rows like that and 2 columns like that, eliminating 2 triads like that from cluster, I also don't change rank of matrix. So number of invariants again remains the same, and so but I have smaller cluster. And then I can keep doing that. So I eliminate those. Then maybe again I will have to come to part 1 because I have single triads with loose ends. Maybe again part 2. Eventually I come to a part where I have 3. I have no 2. You know, even 2 by 2 blocks like that, but they only come as 3 by 3. And that's at the point at which our exclusion principle does not prevent these 3 by 3 blocks to be to have 0 rank. I mean, they can be degenerate. So 2 by 2 blocks cannot be degenerate. Okay. But 3 by 3 can be degenerate, and that's where it comes that at the level of 3 triads, the structures that correspond to 3 interconnected triads which are not connected to the rest of the cluster, where we may have additional invariants, right? So, okay, perhaps let me just illustrate it on one simple example. This frog, this cluster, big one, number of triads 104, number of nodes 178. Basically, I carry out part 1 by eliminating single triads with loose ends 3 times. I can eliminate successively 3 times. Okay, this will result in 2 smaller clusters like that. It will split one big cluster into 2 smaller ones like that. Each of them will have only 8 modes, and 8 triads and 12 modes, right? Much smaller ones. But it turns out that then they're so tightly connected that I won't be able to eliminate 2 by 2 blocks, no 3 by 3 blocks, no 4 by 4 blocks. Only comes to 5 by 5 blocks. So apparently in this example, they're extremely tightly connected. But if I look at these 5 by 5 blocks, I see that they're degenerate. And so I find that I have, the rank of them is 4, turns out. Okay, so each of them of this smaller cluster has 1 extra invariant. So the original cluster has 2 extra invariant with respect to n minus m figure. Okay, right. Okay, so out of these invariants, I mentioned that there's energy, there is momentum, there's some other invariant that was known for Rossby waves, which is called zonostrophy for continuous systems. And they turn out to play important role in the structure of the turbulence cascades. So if I had only 2 invariants, they would, I have a dual cascade picture that energy cascade to low wave numbers, entropy to high wave numbers. But when I have the 3rd invariant, then it turns out that it eats out a big sector of wave number space, and it pushes energy to cascade to not only to large scales, but large and very anisotropic scales corresponding to zonal flows from east to west. And so that leads to, but this is in continuous systems, but it leaves us with a question. Now, if you consider not a continuous system, but we consider large discrete system like this big cluster, what role would quadratic invariants play in this case? Okay, so we see for continuous system, extra invariant dynamically causes has big consequences in terms of direction of cascades. How about now we have much bigger number of quadratic invariants. So this is something to for future investigation. I think important question to model these big clusters either in computer or theoretically. Okay, maybe I'll leave it.
Wonderful.
Yeah.
Thank you.